Bismillahirrahmanirrahim. Assalamu alaikum. I am Farough. Students, we are starting this topic of complex number, the part of your A-level pure mathematics 9709 P3 syllabus. Student, this is considered to be one of the most challenging topic of the syllabus of the course. And that's why I've selected this. And I'm trying to make it simple, not that much complexity. But this is a summary lecture. This is a revision lecture, not in detail, but comprehensive. So please pay attention. Whenever you want, you need to take notes, pause the video, take your notes, then proceed. Whenever you feel that you need, again, repeat that section of the video, again, pause or stop the video and repeat that part here. And this way you get the benefit of this lecture. Before starting the topic, I would like you to know the learning objectives of this lecture. At the end of the lecture, that becomes your checklist. First of all, we introduce the concept of imaginary numbers, then the complex numbers, then a new important number iota or I. Then we learn some mathematics of complex numbers, that is add, subtract, multiply and divide of complex numbers, how to solve equation by equating real and the imaginary parts when we are required to solve some complex equations. Then we need to solve quadratic, cubic or quartic, maximum up to degree 4 equation with complex roots. After this, the concept of complex conjugate, the square root of a complex number, the concept of modulus and argument, the another way of writing a complex number, not just standard form but the polar coordinate and exponential form. Then what about the Argon diagram and few sketches, this is loci, and finally some exam style question. This is the idea, this is the plan for this lecture. And at the end of the lecture, that will be your checklist. You have to check whether you have covered these topics or not. Students asking most of the times why we study complex number. I'm not going to detail about this slide, but just to give you an idea, complex number is not only primarily for the examination point of view. There are real world applications of complex numbers. I've gathered few of them from different sources, mainly from internet. Just for those who are interested to know something about complex number, they can go through it. If you are not interested, you can skip this slide here. So there are few more or many more application. In our syllabus, one thing should be noticed, that is complex numbers are used to find basically roots of certain type of equation, where we could not find the root just by using the real numbers only. So we need to add another type or branch of number with the name of complex numbers. And something about history you find here. If you are more interested, you can Google it and you can get more knowledge about the complex numbers. Now, in the study of mathematics, you come across different types of numbers or different important numbers. In my opinion, the most important number in the study of mathematics is 1. Then it's 0. It's a very important number. You know about pi. You know about e. Not the topic for today, but these are few very important number in the study of mathematics, in the building of mathematics. These are known as the pillars of mathematics. Now you are going to add another number, that is I or iota. We're discussing now. Now students, we know that all the numbers till this stage are real numbers, and real numbers are rational numbers or irrational numbers. Any number, whether you write 2 or you write 3, you write -1, you write half, you write √7, all the numbers come under the category of real numbers, and further division, rational or irrational numbers. Now consider this equation. If I ask you to solve x square equals to -1, if you are working under the domain of real numbers only, you should say, sir, no solution. It's not possible. but that's why we've introduced a new new type of number with the name of negative or imaginary numbers. So since we cannot solve by having just real number only here, we need to introduce a new type of number with the name of imaginary number just to solve the equations, and I can replace a number whose value is root -1. So I can say iota square is -1. This is the introduction of I. I is nothing but the replacement of root -1. For example, if I ask you to solve x square plus x plus 1, 0. You try to solve it, you apply a quadratic formula, and when you use here with the quadratic formula, what are you getting here? -1 plus minus under root -3 divided by 2. You see here again negative part. So I can substitute this negative root 3 as root 3 into -1, and that -1 can be replaced by iota. So now we are introducing a new class of numbers with the name of imaginary numbers to study the complex numbers, right? A new category of numbers. Further proceeding, one thing should be clear at this stage. A complex number is a component of two numbers, real and imaginary. By saying simply imaginary number does not mean you are discussing only complex number. So now onwards, every number is a complex number having two components, an imaginary part and a real part. This is the imaginary part and this is the real part. Like whenever you write complex number in standard form, you have 3 plus 4 iota, and this is equal to basically 3 plus under root -16. There are possibilities that number having only imaginary portion, number having only real portion, and number having both. For example, if you are saying 2 plus 0 iota, it's simply 2. So every real number is a complex number from now onwards. If you're writing here 2 iota, it means under root -4. It has only imaginary part but no real part. But if you're writing 3 plus 4i, it has both the components. Is that clear? So from now onwards, the superset of number will be complex number. It consists of real number as well as imaginary number. Now we have few examples here on the screen. These are your complex number. This is iota basically. So pi plus 1 by 4i, or 2 minus root 3i, or 5 plus 3i. You see, these are the complex numbers, and we have symbol C for this. So can I say now onwards real number is subset of complex number, or every number is a complex number even though it is a real number? Please see this diagram. Before this lecture, this was your superset. These were the numbers you already knew. Every number is a rational test number. Now I'm adding another type of number, imaginary number. So we have a bigger set. That bigger set is known as the complex number. So every number comes under the boundary of complex number, whether it's a real or imaginary or rational or integer or natural or prime or even. Every number is a complex number from now onward. So you can extend your knowledge of the numbers to the limit of complex numbers. Now, when we discuss complex number, we need to understand one thing at the starting stage: how to deal the powers of iota. For example, if you have iota equals to root -1, you know it when I say iota square. So root -1 square is -1. You see here. You need to understand how to deal with the powers of iota. Now, if I am moving towards iota cube, what do you get? Iota cube means you are multiplying I with I square. I square is -1, so you should be getting negative iota. Similarly, if I am going for I power 4, I power 4 means I can rewrite simply this as iota square as whole square. Iota square is -1 with square. What do you get? You get 1. Moving forward, if you are moving to iota power 5, I5 means I can rewrite as factor of I power 4 and I power 1. I power 4 we have just discussed here, it's 1 into I, what do you get? Root minus 1 or iota. You see, iota or root minus 1, iota square, cube and power 4. And for power 5 I'm getting again I, this I and this I. Now if it is power 6, then what do you get? You can rewrite this as iota power 6 as iota 4 into iota square. Iota 4 is 1, you see here, iota square is negative 1, ultimately you got negative 1. So iota 6 is negative 1. What about iota 7? Iota 7, you can break this into, factorize into iota 4 into iota cube. It is 1 and iota cube is negative iota. Ultimately, negative iota. And finally, iota 8 is 1. You see, this important. We have a loop here. I minus 1 minus I 1. I minus 1 minus I 1. I minus 1 minus I 1. Based on this pattern, you can find any power of I. There are only 4 possibilities. I, minus 1, minus I, or iota, or 1. For example, if I give you a few questions here. I power 10. How to solve this? A very simple technique. If you split into I 8 into I square, and that is multiple of 4. So whenever you have a multiple of 4, it is always equal to 1. So we only left with I square, and I square is minus 1. You see the value of this, it is minus 1. I power 15. I can rewrite I power 15 as I12 into I cube. What is I12? Multiple of 4, that is 1. I cube, we have just learned, it is equal to minus I. Check this please. If it is 1 over I, then it is negative iota. I will discuss later on why it is negative iota. If it is I power 69, now I can rewrite I power 69 as I 68, the multiple of 4 into I. This is always 1. What is left? You left with I. And same way, how to solve this? So please practice these questions and learn how to solve the powers of iota. This is the just introduction of the concept, imaginary numbers, and how to deal with the power of iota. And all the numbers are complex number, even though it's simply a pure real number, because real number is a subset of complex numbers. Now we have few mathematical manipulation here, properties here, like root minus 36. You should learn how to write this. I can rewrite root minus 36 as 36 times root minus 1. This is replaced by I, and this is simply 6. Same is here. If it is x squared plus 9, I shifted there on the other side. Now root of negative 9, not possible for real number, but now we are discussing complex numbers. I can say it's plus minus under root negative 9. Root negative 9 you can rewrite as 9 into root negative 1. That becomes iota and 3. If you apply here quadratic formula, you get this result. Minus b plus minus under root b square minus 4ac divided by 2a. So minus 6 plus minus negative 64 divided by 2. Negative 64 I can rewrite as negative 6 plus minus 8 iota, because 64 is the square of 8 and negative 1 replaced by iota. If I take 2 common, minus 3 plus minus 4 iota, same is the result. Similarly, if you are adding complex number, you add corresponding numbers. Real part with real part, imaginary part with imaginary part. For multiplication, you multiply 8 by 3 and then 8 by 2. I'm going fast because the revision class only. Iota into 3 into iota, we have just learned iota square, which is negative 1 minus minus plus. See why I got plus here? 24 plus 2, 26, and that's the result. You can pause the slide here, pause the video here, note down these examples, get the idea clear, then you can move forward. Now further detail of complex number multiplication. For more practice, how to multiply a complex number as you already do in basic algebra, just open the brackets. 2 into 4, 8. 2 into 2 is 4 iota. 3 into 4, 12. Now you see I into I square, which is negative 1 minus minus plus. So that becomes plus 6. 6 plus 8, 14. Now we have few examples here. The answers are already there, but you can pause the video. I'm not solving these. You can pause the video, solve the examples, check your understanding, see the answer, then proceed. The answers are there. If you have already solved, you can check these answers. I'm not solving these. You try to solve this yourself. And basically here we have to check your two skills. One, how to multiply a complex number, and secondly, how to deal with the powers of iota. Based on those two skills or those two concepts, you can solve these examples. And we have more examples here for multiplication. You see here, when I say z square, I have to square it. 1 plus iota square, just applying the binomial expansion technique. A square 2ab plus b square. Iota square is minus 1. Minus 1 plus 1 cancel out. You get 2 iota. So I'm leaving this for you and you can solve. For example, a very big power of this. I can rewrite this as the closest multiple of 4, which is 2000, and remaining is cube. Whenever you have power multiple of 4, you always get 1 into iota cube, and iota cube is minus iota. So don't go fast, pause the video here, spend a few minutes here, solve all these examples, get the idea clear, get the concept clear. If you are getting the right answers, then proceed. Another important point in the study of complex number is the complex conjugate. And this is very important concept, very important component of complex number, in fact. How we define a complex conjugate? If you have a complex number in the standard form real plus imaginary, then conjugate simply changing the sign of your imaginary part. Plus is minus. If it is negative here, that would be positive. That is known as the complex conjugate. And most of the authors use Z steric to represent complex conjugate. In some of the books or authors, they write Z with bar. So you should learn the language also, the symbols also. So Z conjugate or Z bar meaning complex conjugates. So for x plus y iota, conjugate is x minus y iota. And for x minus y iota, conjugate is x plus y iota. That's why I use the word complex conjugates. Now you should learn few properties of complex conjugates. I'm not going to detail the proof of these properties, but you should remember, memorize it, because these are commonly used when you solve the questions from the book or the past papers. Whenever you multiply two complex conjugates, you always get x square plus y square. Very simple to understand. If I have a complex number, this is my conjugate. You have the format of a plus b, a minus b, that is equal to a square minus b square. X square is there, I square is minus 1 minus minus plus, y square is y square. Note down this property. Whenever you multiply complex conjugates, you get real square plus imaginary square. Similarly, whenever you are adding a complex to a conjugate, you get twice of real number. You are adding a complex number with its conjugate. You see imaginary part cancel out, ultimately 2x, twice of real. Similarly, if you are subtracting a conjugate from complex, you get twice of imaginary. If you are subtracting complex from the conjugate, this is now cancel out, ultimately I by iy plus 2 imaginary, twice of y. Clear? Similarly, students, if you have to multiply two complex numbers, then find the conjugate of that complex number, and then you separately multiply the conjugate of the same. I'm leaving this for you. For example, I'm just writing example here to check your understanding. Suppose if I have a complex number this and a complex number, suppose this. Now multiply these two and find the conjugate. Then first find the conjugate, then multiply, and you see both the results are equal. Learn these properties, make a summary of these points. You must be having with you a notebook. Write down these features, these properties of complex conjugates. If you raise a complex number by any power, here I'm writing square. If you raise a complex number by square and then find the conjugate, and then if you conjugate the complex number then squaring, you get the same result. You want me to solve this, an example for you? Okay. If I'm writing here, please see here, if I'm writing here a complex number, a simple complex number, suppose 1 plus 2 iota, its square value is 1 plus 4 iota, and iota square is -1 into 2 square 4, -4. I am getting -3 plus 4 iota. The conjugate of this complex number, that would be 3 minus 4 iota. So I first squared, then found the conjugate. Now if I first write the conjugate of this number and then square, so conjugate of this number then square, so conjugate of 1 plus 2 iota is 1 minus 2 iota. Now please square it. If you square it, what do you get? This is, 1 minus 4 iota. Iota square is -1, minus plus. What do you get? Please, you get -4. Ultimately, you're getting -3 plus 4, -4 iota. Same results. Note down these properties, please. Similarly, if you're multiplying with a number, a real number, twice of complex number, thrice of complex number, then find the conjugate. Or if you first take the conjugate of that complex number, then multiply with any real number, you get the same result, where k is a real number. And one more property, and I think in 2012 or 2013, I don't remember the exact year, a question based on this property was asked in the examination, and most of the students found it very challenging or difficult. They could not manage. If you are subtracting an imaginary number from a complex number and then take the conjugate, or if you take the conjugate first and adding that imaginary number, results are same. Please try to apply this concept. Practice it, make an example and get the idea clear, and please make a summary of these properties of complex conjugates. Now these are few examples for you, and the basic idea in all these examples is one formula: z into z conjugate always equal to x square plus y square. You don't need to show the detailed multiplication here. Just apply this property: real square plus imaginary square. 3 square 9, 2 square 4, you get 13. 3 square 9, 2 square 4, you get 13. 5 square 25, 4 square 16, 41. See here, 1 square, and here the coefficient is 1. 1 square plus 1 square 2, and 4 square 16, 2 square 4, and 20. So if you learn this property, you need not to do the complete multiplication. The next idea, how to do division, and here we have to apply the concept of conjugates. Your first application of the concept of conjugates. If you see an imaginary part, if you see iota part in denominator, what should you do? You first remove that imaginary part from denominator, multiply and divide by the conjugate of denominator. You see here 2 plus 3 iota, I multiply and divide by 2 minus 3 iota. Here you have complex into conjugate, that's equal to x square plus y square. 2 square 4, 3 square 9, and ultimately you are getting 13 in the denominator. If you multiply the numerator, 2 into 26, and 3 into 26 with negative. Now you can write in single fraction, but the better idea to split into real and imaginary components separately like this. This way you can perform division of complex number. Note down please. If you have a single term that is just imaginary part in denominator, you can just multiply without changing the sign. There is no issue. Not necessarily multiply with the conjugate. You may use conjugate, or you simply multiply with 3i and 3i, or even though you multiply with I and I, that's equally fine, because by doing this you just eliminate I from denominator. I into I minus 1, 3 into 3 is 9, this is minus 9, and here we have 78 iota. You got the idea. You need to remove imaginary part from denominator. Now here we have few examples. The solved example with the answers. Pause the video here, solve it, try it, do it yourself. I've given you few practice material after every 3-4 slides. So you just check your understanding, check your knowledge, whatever you have revised. Again, I repeat, this is a summary lecture, a revision lecture. I'm not going to detail for each and every concept. Now, how to show complex number on subgraphs, the complex planes. Another name is Argon Diagram. So what are we doing here? We are using the same properties, the concept of Cartesian graphs, but only one change: the labeling of the axis. Instead of x-axis, we have the real axis. Instead of y-axis, we have the imaginary axis. So we have imaginary. Suppose you have a complex number 4 plus 3 iota. So this real part you have to move along x-axis. Real part is here 4 unit, imaginary part is 3 unit, and you are here. This is your complex number. I can show the vector. And z is commonly used symbol for a complex number. Not necessary, you may use other symbol, but most of the cases you find the symbol z to show a complex number. Instead of writing the whole complex number showing the components of real and imaginary, you can use the symbolic language. X-axis become your real axis and y becomes your imaginary axis. I have discussed, and this is known as the Argon diagram, named after this mathematician Jane Robert Argon. So we call this as Argon diagram. So I'm sure now you know whenever we talk about the Argon diagram, it means we are talking about the sketching or the plotting of complex numbers. This is something about historical facts, and the symbol we are using here, z, for complex number. Now, how to plot? You have to see the quadrants also. For example, here you have imaginary part positive and real part both positive. Here both real and imaginary positive. So how to show this? Now you can show the positions. This is real positive, imaginary positive. You see real positive, imaginary positive. This way you identify the quadrant also in the Argon diagram by seeing the signs of real and imaginary part. You see here real part is positive but imaginary part is negative. That should be in the fourth quadrant. Real part is positive, imaginary part is negative. -1 plus 2 iota. Real part is negative, imaginary part is positive. Second quadrant. Please learn how to plot in Argon diagram in different quadrants. And finally, both negative means third quadrant. Is that idea clear? And you should understand the meaning of real and imaginary component. You should understand this use of signs to decide the quadrant. Now, when you have a Argon diagram and you have a complex number here, the distance of this complex position from the origin, this gap is known as modulus. This length is known as modulus. So when I have the geometrical meaning of modulus of complex number, just applying the Pythagoras theorem here, this is x or real part, this is y imaginary part, x squared plus y squared, you get, we have the symbol of two vertical parallel lines to show the modulus of complex number. And this is the angle of complex number with the positive real axis known as the argument. And here we have the argument, tan inverse, opposite over adjacent, imaginary over real, this is the argument. So whenever you have this word argument, it means it's the angle with the positive real axis. and you should know in which quadrant. Please note down this basic property at the beginning. If you have a complex number in the first quadrant is simply theta, your basic angle. In the second quadrant is pi minus theta. Now we have a convention, we have a practice only to write the complex argument between negative pi to pi. This is known as principal argument. In most of the cases, examiner requires this. Write the answer in the form of, in the range domain of minus pi to pi. So if you are in the first two quadrants, you write theta and pi minus theta. But if you are in the fourth quadrant, it means you're moving clockwise. That angle becomes negative theta, and here it is theta minus pi. So please note down this. This way you can find the angle of complex, the argument of complex numbers. These rules are important to be learned. Is that clear? Now moving forward. Now about the representation of conjugate on the Argon diagram. Now if I have a complex number 2 minus 3 iota, conjugate is 2 plus 3 iota, and oppositely if I have 2 minus plus 3 iota, the conjugate is 2 minus 3 iota. And they form an interesting pair on the Argon diagram. Now this is the sketch of complex conjugate, you see, of 2 plus 3 iota, and this is 2 plus 3 iota, the above one, the upper one, and the lower one is 2 minus 3 iota. This is 2 plus 3 iota, and this is 2 minus 3 iota. And it is basically reflection in the real axis. Now we have symbol Z conjugate, you know it. And when you add complex with the conjugate, you get twice of real. I've discussed with you. When you multiply, you have x square plus y square. Now I can say you multiply two conjugate pairs and you are getting square of modulus, because we have learned the symbol of modulus. And the modulus of complex, this number, complex number, and its conjugate, both are equal, having same length. But the argument you see here, a negative sign. If this angle is suppose theta, so that becomes negative theta. Learn this property of complex conjugates. Now we have a few examples. If you have a complex number 1, its modulus is 1, argument is 0, y 0, 1 means purely real number, like this. So you have 0 angle. If it is negative iota, somewhere here, negative 1, imaginary axis. Modulus is 1, but argument is negative pi by 2. Please check your understanding. If you have negative 1 plus iota, negative 1 and plus iota, somewhere here. So this length is root 2, apply Pythagoras theorem, x square plus y square. But what about this angle? You apply the formula tan inverse real over imaginary, ignore the signs first, you get pi by 4. In this quadrant you have pi minus theta. So what about pi minus pi by 4? You get 3 pi by 4. If you have both negative, real part negative, negative 5, imaginary part negative, negative 2, somewhere here you have a complex number, you need to find the modulus. Square of 5 is 25, square of 2 is 4, take the root, you get 29. Now find this basic angle first, tan inverse 2 by 5, and here we have theta minus pi. You see angle is clockwise, the negative angle. Pause the video here, get the idea clear, because these are among few things where students normally make mistakes. Now moving forward, you have so many examples. Again, similar question. You have a complex number there, so real part, check modulus argument. You have different complex number, these are the given values and these are the required values. Find the modulus argument. Pause the video, do the question, practice the examples and get the idea clear. And you should learn the use of calculator also, how to find modulus and argument. Now at this stage, I want you to learn the use of calculator for complex numbers. You see on the screen the calculator is there. You first press this option of menu and number 2, complex. You are in the area of complex numbers. Select this. You see this symbol of I on this screen. Now suppose I have a number minus root 3 minus iota. You see the pointer, minus root 3 minus iota. how to feed this. Negative root 3. Cursor forward. Negative. For inserting iota, you have to use this key of E and G. You see here iota. The number is there. Now, if I press this key of O, P, T and option, you find the argument, the angle with the choice of number 1, option 1 press, answer, and you get the angle negative 150 because I've set in the degree mode. If you want to set the radian mode, shift, setup. At number 2, you have angle options in radians. Now what are you getting? I'm doing again option of argument minus root 3 cursor forward minus, and here we have iota, close the bracket and get the angle. Is that clear? To find the modulus, you have this key of ABS, absolute value. Press shift and ABS, absolute value. You have the complex number minus root 3 cursor forward minus iota, and this way you get the value of, you see, 2. Please practice all these questions manually and also with your calculator. This way you learn at least this portion in your calculator, how to deal with the complex number. Even if you want to divide two complex numbers, you can do very quickly. See here, if I have 2 plus iota, a complex number in numerator, divide by 5 minus 9, and this E and G gives you iota. Just press this key of equal and get the result. In examination, you can check your answers, your working, your result effectively and efficiently. Hopefully the idea is clear. Please practice. Moving forward. Now one more thing about the complex numbers. Another form. You see the title here, modulus argument form of complex numbers. This is the standard form of complex number. Sorry, it's not iota, it's not x squared, it's x plus iota y. Now we want to convert that complex number into some other form. So you need to find the modulus x squared plus y squared in the root. You may use symbol r for this. Normally you find this in your books. And for argument, you can use theta. For angle, you get this angle argument. Now if I extend this line, apply the trigonometric property, the basic trigonometry, this real part you can rewrite as r cos theta. Please pay attention. And this vertical height of the imaginary part you can write as r sin theta. So if I replace x by r cos theta and y by r sin theta, then you see what you get. You have another way of writing the complex number. I've taken r common, cos theta plus iota sin theta. This format is known as modulus because r is modulus, theta is argument. Modulus argument form, or another name is the polar coordinate form. So now you have learned two different ways of writing a complex number, standard form and the polar coordinate form. You need to know the argument and you need to know the modulus, and then you can find the or write in this form. Secondly, you have few examples here. Now first complex number is minus I. You see only real part, no imaginary part. The modulus is 1, argument is pi because real is negative. And how to write negative 1 is equal to modulus is 1, argument is pi, replace the values. If you simplify this, you get again minus 1. Same for the next one. Your modulus is 1, but the argument is pi by 2 because it's vertically up. If I draw this, it's vertically up, pi by 2. And you can write in this form. Here you have modulus 1 squared plus 1 squared root 2. And then argument tan inverse 1 over 1 is pi by 4. And this is your. And please do solve each and every example to get your idea, your concept clear about these numbers. How to deal or how to convert standard form into modulus argument form. Now moving forward, you have few more examples. You can do yourself. For every number find the modulus, for every number find the argument, and write in that required form r cos theta plus iota sin theta. I've already solved these, but I want you to solve yourself first. Pause the video here and then check the results. And try to sketch also. You see, real part positive, imaginary part negative. That should be in the fourth quadrant. That's why the angle is negative pi by 4. Please connect the Argon diagram with your values. You should understand the location and you should understand how to write the argument. You can further write this in one more step, a simplified version of this also. Cos minus theta, all of you should know it's cos theta. You can write cos pi by 4. I have no objection here. But sine minus theta is negative sine theta. The second last line and the last line give the same thing. You may write in this way also. But when you write with the same sign of argument, that's a better idea because that will give you about the sign of the argument, the quadrants. The next example was this. Minus root 3 minus iota. Find the modulus. This is a mistake here. Negative 1 square. And ultimately you are getting 2. And find the, whenever you find the argument, ignore the sign first because signs are used to select or decide about the quadrant of the location of the complex number. Now you have this angle you can show in the graph. You see here we got tan inverse 1 over root 3. You should know it is pi by 6. Now pi by 6 minus pi. Remember these rules, theta, pi minus theta, negative theta to write the arguments. So here I got theta pi by 6 minus pi. The result is negative 5 pi by 6. Because we have a practice or we have a convention to write the argument in this range. Another number, first you need to multiply the two complex number. I've used the same two complex number which I used in part A and B. So I already know their modulus and argument, Now I'm adding one more property here. If you are multiplying two complex numbers and then find the modulus, or if you simply find the modulus of individual complex number then multiply, result is same. Note down this important property. Z1 into Z2 with modulus is same as Z1 Z2 modulus, and this property can be extended to more than two numbers. You got the idea? If you multiply any two or more complex numbers, getting a new complex number and looking for its modulus. Another idea, if you first find the modulus of individual complex numbers then multiply, result is same. And about the arguments are always added when numbers are being multiplied. Please note down this property. Argument of Z1 into Z2 is equal to argument of Z1 plus Z2. This way you can easily handle the multiplication of complex numbers. If you first find the modulus and argument and then apply the property and then use this form of modulus argument form. You see this here. Plug in the values. One thing I think I went very fast about this. Wait. This was 13 pi by 12 negative and that is more than 1 pi. More than negative pi. So when you are moving clockwise, more than negative pi means you are in the second quadrant somewhere here. So if I add 2 pi to this, it means I want to move anti-clockwise. Please pay attention. Negative 13 pi by 12 adding to 2 pi, 12 times 2, 24 minus 13, you get 11. You got the idea? If you are in the first and second quadrant, take the angle anti-clockwise. If you're third and fourth quadrant, take the angle clockwise. Please note down this. This way you got the result. One last example. The same number I've used, you already have its modulus and argument. You already have the modulus and argument. My request, pause the video here. Try to do it yourself. You may divide the complex number by using the conjugate, or you may apply another property because in the form of r cos theta plus iota sin theta, what do you need? You need the modulus and the argument. So if I need the modulus of this new complex number, I can simply divide the modulus of numerator by the modulus of denominator like this. That saves your time because you already have modulus 2 root 2 and here you have 2. Learn this property. If you are dividing two complex number and to get a new complex number and looking for its modulus, you can easily divide the modulus of numerator by the modulus of denominator complex number. And about the arguments, you subtract the argument of denominator from the argument of numerator and check whether it is above 1 pi or less than 1 pi. It's already less than 1 pi. There's no need to do any further adjustment. It is in the required quadrant and we get the result. This way you can convert modulus into you can convert a complex number into modulus argument form. I have moved very fast. Pause the video, practice, then move to my next section. Now the last thing for this first lecture, how to find the square root of a complex number. This is again a very common requirement in the past papers. Find the square root. We are looking for a number whose square is minus 11 minus 60 iota. Right now I don't know the number. So I simply start with this assumption that number is a plus b iota. For example, if the square root of 4 is 2, can I say 2 square is 4? So if the square root is a plus b iota, can I say a plus b iota square is that number? If you expand the left side with the binomial, what do you get? And you already know iota square is minus 1, that's why I put negative sign here. Now what we do here, the comparison, real term with real term. We see a and b having no iota along with these two numbers. I equate a square minus b square by negative 11, and this is imaginary number 2ab iota minus 60, and we have got two equations with two unknowns. Solve them simultaneously. You can rewrite b as negative 30 over a, substitute in the first equation here, 30 square is 900. You have a equation of degree 4. You can use the concept of disguised quadratic. That is, you can rewrite this as a square. Sorry, if I take a square as suppose k, so can I write here as k square plus 11k minus 900 and factorize it or use quadratic formula? The factors are k minus 25 and k plus 36. And k is replaced by a square, so a square minus 35, a square plus 36. Now if I equate a square is equal to negative 36, it means I am getting imaginary number. And in my assumption, my complex number was that. So in this assumption, both a and just b, not iota b, a and just b both are real. And here if I am getting a imaginary, I just reject it, reject this option. So when a squared minus 25 is 0, the value of a is plus minus 5. Substitute the value of a here. 30 over 5 is 6 with negative, and 30 over negative 5 is 6 positive. You see, I got the value of b. So the complex number a plus iota b should be this and this. And please at this stage note down one thing that will be used in later examples. Whenever you have square roots, please note down, whenever you have square roots, these square roots always form rotational symmetry of order 2. In simple language, if your one of the square root is coming in this quadrant 1, other should be somewhere where the angle between these two is 180. Note down this property and check with my examples. If one of the complex number falls here, square root, the other square root should be with the angle difference of 180. It's very important property, how to relate two square roots. The square roots form rotational symmetry of order 2, because if I make a circle, you see this circle giving you rotational symmetry of order 2. Pause the video. If not clear, repeat this part, note down, and then relate with my future examples how to relate this property with the square roots. Whenever you find the square roots, you always get two square roots where the angle differ by 180 or pi. Doing one more example. The same technique. I assume that my square root is a plus iota b, square it with the binomial. If I expand with the left side and cross multiply this 400, I've taken LCM on the right side just to make my comparison simple. So 4a square minus 400a square minus 400b square is negative 161, like this. And imaginary part is 4 times 2 is 800 AB, and here we have 240. So can I say B equals to, with cross multiplication, 240 over 800, so you get 3 by 10 positive. Substitute the value of B here, 3 square 9, 10 square 100. 3 square 9, 10 square 100, and then open the bracket. You want me to solve 400 with this a square minus 9 over 100 a square. If you open the bracket, you get 400 a square, 4 and 0 0 cancel out, 4 times 9 36 over a square. You see the same is there. Now make degree 4 equation. The same technique, disguise quadratic. I can substitute a square suppose by p, so that becomes 400p square plus 161p minus 36. You can use your calculator or factorization or quadratic formula and you get these results. 25p minus 4, 16p plus 9. Again, in this case, when you equate a square by negative 9 by 16, you get imaginary value of a, which is not allowed because we have assumed a as the real number. Reject this, invalid. So we got the value of a from here. 4 by 25 is a squares. A becomes 2 by 5 plus minus. And finally, put the value of a here to get the value of b. Pause the video and please do it yourself, and your final complex number having square root this. Again, you see here the roots, if you plot, they form rotational symmetry of order 2. If this is the value 2 by 5 plus 3 by 4 iota, this is the value of negative 2 by 5 minus 3 by 4 iota, and difference of pi. So dear, this is the end of my first lecture. I am having more because the topic is not covered yet. I know I have moved very fast because this is the requirement, because we are doing the revision only, not in detail. If you need any further help, go through this lecture again, take your notes, refer to the book or the past paper, right? Now student, you have learned the technique of finding the square root by algebraic method, and we will be discussing more techniques of finding the square root by De Moivre theorem or exponential method when we do lecture number 2 or number 3 later on. Right now I am giving you a very smart or quick method of finding the square root, and that can be used only for the checking purpose. In examination you have to show detailed working, and this can be used in some other MCQ type of testing. You see here, if your complex number is x plus y iota and the square root is a plus b iota is your square root. Now to find the value of a of the square root, a simple technique, a simple formula, one-step method. You take the real part of that number whose square is required and you take its magnitude or the modulus value and divide by 2. That is the a square. If you take the root of this, you get the value of a. And the value of b you can find easily and quickly. You divide the imaginary part of this number by twice of a. You see, don't need to show the detailed step, but that is not allowed in your P3 examination. It is a very smart technique. You can check the previously done examples, what I did in the last few slides. Like we found the square root of minus 11 minus 60 iota. Its real part is minus 11. Its modulus is 11 square plus 60 square. You write here, divide by 2, take the root, you get the value of a. And when you get the value of a, you can find the value of b easily. That is minus 60 divided by 2a. Please check this formula, this method, is it functional, workable or not yet. We did this example also, and you know the answer of this example, and you can check by using this shortcut or smart method or quick method of finding the square root here. Here I am ending my video, and then we'll be proceeding to the next lecture. Thank you dear. Allah Hafiz.